All right, so back in chapter 11, last time, right, we were talking about relations and we ended with talking about equivalence relations. What's it take to be an equivalence relation? What three things?
You gotta be reflexive, symmetric, and transitive.
Reflexive, symmetric, and transitive, absolutely. All right, so equivalence relations, like I said last time, they're super important. They come up a heck of a lot in math. So we're going to get a couple definitions related to that. Here's a big important one called equivalence class. So this may look a little crazy, but we're going to take a relation. It has to be on a set A because I'm dealing with reflexive, right? So it has to go from A to A. Can't go from A to B. So this notation here, that R with that kind of bracket around A, or in fact, we'll sometimes just do the bracket around A if there's only one relation. I don't have to say what it is. It's the set of all things related to little a. Since I'm symmetric, it doesn't actually matter which side I put the X on, right? Because I'm symmetric. If I have X related to A, I get A related to X. Okay, but this is the way we're going to do it. This is the way most people define it. So we'll call that the equivalence class of A. So let's just take a second and see if we can understand what this is saying. All right. So it says take the relation M from example 5. Well, what was our relation M? M was the stuff that was the same modulo 3. Okay. So what are two numbers that are the same modulo 3? Well, crickets. Well, what about 4 and 1, right? Are those equivalent mod 3?
Yep.
Yeah, because 3 divides 4 minus 1. So what that means is that 4 is an element of the equivalence class of 1, right? Because he's related to 1. But we're symmetric. So that also means 1 is an element of the equivalence class of 4. Okay. Well, let's think about that equivalence class of 1 and think about what type of numbers would be in there. So X is related to 1, means X is congruent to 1, mod 3, means 3 divides X minus 1. Well, that means X minus 1 equals 3K, right, for some integer K. So what form does X have? 3K plus 1. Yeah. So it's 1 more than a multiple of 3, right? Makes sense, because then when I subtract 1, it becomes a multiple of 3. Okay, so it's 1 more than a multiple of 3. So the equivalence class of 1 is actually all numbers of that form, all integers of that form. So we'll have stuff like, leave space for the negatives, but 1, 4, 7, 10, right? Now the negatives, we're going to have -2, -5, right? That way, because my multiple of 3 would be -6, and -5 is 1 more than that. Okay. All right. So this one also asks for the equivalence classes of 0 and 2. Well, what type of things are going to be related to 0 modulo 3? Multiples of 3, because I need X minus 0 to be a multiple of 3. So we can even write it this way, 3n such that n is an integer, right? It's the multiples of 3. Different color, I guess I'll do red. All right. Equivalence class of 2, based on this, what form do you think stuff in the equivalence class of 2 will have? 3 divides x minus 2. So x has to be a multiple of 3 plus 2, right? So we can write this two ways. We could say 3k plus 2, such that k is an integer, or we could list it out. So we'd have stuff like -4, -1, 2, 5, 8, and so on. All right. So this is kind of interesting here. Pick any integer you pick, it's actually going to be in one of these equivalence classes, right? So if you say, well, what about 27? I'm going to say that's a multiple of 3, right? You say, well, -100, say, well, that's 2 more than a multiple of 3, okay? A million would be 1 more than a multiple of 3. So we've actually covered all the integers here in these equivalence classes. So here's a question: will I ever have something in 1's equivalence class that's also in 0 or 2's equivalence class? Good, no, because either it's a multiple of 3, it's 1 more than a multiple of 3, or it's 2 more than a multiple. It can't be 2 things at once, right? Think of it this way: when I divide by 3, I either get 0, 1, or 2 for my remainder, okay? All right. Now, one more thing to think about. The equivalence class of 4, we already said 1 is in it, but let's think about that equivalence class of 4. So switch colors again. So I need x minus 4 to be a multiple of 3. So x equals 3k plus 4. Does that fit in any of the ones I already have? It goes back to being 1 more than a multiple of 3, right? Yeah, because this is 3k plus 3 plus 1. So it's 1 more than a multiple of 3. So the equivalence class of 4 is exactly the same as the equivalence class of 1. They're related to all the same things. Okay. If something is related to 1, it's also related to 4. Okay. And that kind of makes sense. I mean, our equivalence relation is symmetric and transitive. So if 1's related to 4 and 1's related to 7, flip that to get 4 related to 1 related to 7, right? So 4 and 7. So it makes sense, okay, that they'd be related to all the same things. All right. So that's the idea of equivalence classes. Now, let's actually prove some facts about them. So first, we want to talk about the fact we just said and prove it. Suppose I have an equivalence relation, or arbitrary equivalence relation, on some set A, and that I have 2 elements of A, then their equivalence classes are actually going to be identical if and only if they're related. So if they're related, the equivalence classes match. If they're not related, the equivalence classes aren't equal. In fact, they're actually disjoint. Okay, they can't have anything in common, but we're not proving that. Okay, so let's go ahead and prove this. And I put outline. When I put outline, that means I don't feel like writing all the sentences, so we're just going to write the logic. But in a real proof, you'd convert all these to sentences. Okay, so let's go with this direction first. So we're going to assume A and B have equal equivalence classes. Well, what is the first property an equivalence relation always has? Reflexive. So reflexive, that's going to give me A is related to itself, right? ARA. So A is an element of his own equivalence class. Yep. So, but what did we assume at the beginning?
The classes are equal.
Classes are equal. So A is in the equivalence class of B. But what does that mean? What does it mean to be in the equivalence class? They're related. So A is related to B. That's the easier direction. The other one's not bad either, but
Is there a class that we're gonna have to take that like deals with this too?
well, equivalence relations come up in a lot of math. And we'll see why as we keep going, why they're important, but they're very, very useful. All right, let's go the other direction. So we're going to assume A is related to B. Now I want to show equivalence class of A equals equivalence class of B. Those are sets. I'm trying to show two sets are equal. So what do?
Mini proofs.
Mini proofs, subset both ways, right? So, all right. So first we're going to let X be an element of the equivalence class of A. And we need to show that then it's also in the equivalence class of B to get subset that direction. All right. Well, what's that mean? That means X is related to A. But what did we assume for this? A is related to B. So what property am I going to use? Yeah, transitivity. That'll give me X related to B, which means X is an element B, equivalence class of B. So equivalence class of A is a subset of the equivalence class of B. All right. Let's go the other direction. So we could use X again since we're done with it, but I'm going to use Y just to be super explicit. So let Y be an element of the equivalence class of B. Well, that means Y is related to B. Yeah, so you're right. How do I know B is related to A?
Because it can go, because A is related to B, it can go backwards.
Yeah, by symmetry, by symmetric. So then we can use transitive to get Y related to A, which means Y is an element of the equivalence class of A. So equivalence class of B is a subset of the equivalence class of A. So everything in A's equivalence class is in B's, and everything in B's is in A's. Therefore, they're the same. Thus, A equals B. So this is kind of what we were saying with that equivalence class of 1 and equivalence class of 4, okay? That they end up being the same thing because they're related, all right? So that's actually always true. Did you have a question?
Yeah. Can you repeat the last thing you said? Like, they're always related.
So if things are related, they produce the same equivalence class. Or if things have the same equivalence class, they have to be related. Yeah.
So the only time we can use these, I don't even know what the proper name is, equivalence relations, the transitive, reflexive,
Mhm.
and symmetrical, is whenever we know for a fact that it is in a equivalence relation. I can't.
Correct. Yeah. No, you're learning the words. I get it. Yeah. Because this problem started, suppose R is an equivalence relation, I was allowed to use reflexive, symmetric, and transitive. You may have some problems that just say, suppose R is a transitive relation. Then you can use that fact, but you can't use reflexive or symmetric, obviously. But for an equivalence relation to work, for equivalence classes to make sense, you need all three. Notice we did use all three in our proof. We used reflexive and symmetric and transitive. What do you mean?
Whenever you're trying to do the one with the equivalence class, will you end up
So
using all three?
in order to have an equivalence class, you need equivalence relation, but if you are proving a tiny specific thing about equivalence classes, you might not need all three properties. But since we were proving a big broad thing here, it ended up using all three. Yeah. But yeah, it just depends on the proof. And sometimes it's kind of hidden because some of you may have just said B related to A without recognizing, oh, I just used symmetry on the A related to B, right? Okay, so a related idea here, then, and we're going to tie these together, is the idea of a partition. You may have heard this word before. You may not have. Here's the idea. Partition of a specific set, okay? You take a set, or we could even change that to the word collection, if that makes you feel better, of non-empty subsets of A, such that the union gives you everything, but there's no overlap between those subsets. So union gives you everything, but there's no overlap. All right, so we'll do the math notation in a second, but let's look back up here at our equivalence classes up here. Notice we said that the equivalence class of 1, 0, and 2, give me any integer I want. He's in one of these. You pick an integer, it either has remainders 0, 1, or 2 when you divide by 3. So it's in one of these, okay? So if I union these together, that means they give me all integers. And we also said they'll never overlap. So I could say that these kind of split the integers into 3 groups, right? I'd have 0, 1, and 2, 3, 4, 5, 7, 8. I could do negatives as well. -1, -2, -3. That's what we mean by a partition. We've actually been using a couple different partitions all semester, even and odd. That partitions the integers because it's either even or it's odd, but it's never both, right? So that covers everything with no overlap. You could say that with positive, negative, or 0. That gives me 3 different groupings. One of them is tiny because it only has one thing, but 3 different groupings, no overlap, cover all real numbers. Complements, yeah, any set and its complement will give you a partition. You have 2 things, they cover everything with no overlap. Okay, that's what we mean by a partition. So let's write that in math notation, what we're saying. So we have, let's write our collection will be a bunch of sets. I guess we can call them B, okay? Yeah, I guess I'll just say B of I. So I could have 2 things we said, right? I could have 20, I could have 100. I guess technically you can't have infinitely many. Okay, it's kind of weird, but you can. So this is what this is saying. The union, if I take everything out of C, needs to give me all of my original, in this case was capital A, and B of I intersect B of J has to be empty, and we'll say if I is not equal to J, okay? So sometimes instead of writing it that way, books will write it this way. BI intersect BJ equals the empty set, or BI equals BJ. And that is kind of nicer notation, that purple one, for the equivalence classes we just did, because like equivalence class of 1 equals equivalence class of 4, right? So they'd be that second type. They're actually the same set, okay? All right, so here's the connection that we've kind of already seen. Equivalence classes make a partition. As long as you have an equivalence relation, those equivalence classes are going to form a partition. So let's look at that. Again, we're going to outline the proof. All right. So let's see. Let's start with, well, a partition, I need two things. I need the union to be everything, and then the intersection is either empty or identical, right? So let's work on the union part. So let's take the union, all equivalence class of A, such that A is an A. I guess let's put in front of this want that to equal capital A. Which direction is our subset kind of obvious? Since A is our main universal set. You're getting too specific on me. So I just mean the union has to be contained in capital A, because those are the only things in existence for this problem, right? So union, subset of A, duh. Now you would never turn in a proof like this, okay? We're just doing an outline. This would be your scratch work before you write up your proof in complete sentences. Okay, but we need to do the other direction. So let X be an element of capital A. I need X to be in that union. How do you get in a union? What's it take to be in a union? You got to be in any one of them. Well, what equivalence class is X guaranteed to be in? His own. Yeah, because everything is related to itself. All right. So X is an element of X since X is related to X. And again, there we used reflexive, right? So X is an element, the union of all those equivalence classes, because one of those actually is him. So then we have A subset of the union, right? Which means they're equal because I got subset both directions. Okay. Now, the thing to be careful about here, that equivalence class that X is in, there could be another name for it. Like 1 would be in the equivalence class of 1 in that example we did. 4 is also in the equivalence class of 1. It just happens to be the equivalence class of 4, right? I can call it that because they're the same thing. So these are not a separate new grouping for every single element of capital A. You get a lot of repeats, is my point. Because when I take the equivalence class of 1, if I'm doing mod 3, 4, 7, 10, they're all actually the same set. I'm just taking the same equivalence class over and over. Okay. All right. So we got the union part. Now I need the disjoint part. In fact, you can call this pairwise disjoint. Have you guys seen that phrase yet? You saw, oh yeah, I bet in 407 in probability, you see that a lot. So for those of you that haven't seen it, that's what pairwise disjoint means, okay? All right, so let's show that. So So let's consider equivalence class of sum A intersect the equivalence class of sum B. If this is empty, we've got what we want, right? So we're going to do that classic kind of two-case split where if equals the empty set, we're done.
I really just put straight up.
So assume it does not equal the empty set, and let's see what happens. If it's not empty, I mean, go way back to when we first did sets. What's it mean to not be empty? Something's in there. I don't know what it is. Something's in there. So we have an X in there. Well, what's that mean about X when it comes to little a? X is related to A. What about B? X is related to B. So what does transitivity give? Well, use symmetry, and then A related to X, X related to B, and we then use transitivity to get A related to B. Look at the top of the page. What did we prove? A related to B means equivalence classes are equal. So either they have nothing in common or they're the exact same set. That's what we wanted, okay? Pairwise disjoint. Yep. Yep. All right. Oh, good. And we have time to do, I'm going to add one more thing, but let's do this summary first. And then on the back, we'll do one more thing that's related to this. That's cool. So to prove a relation is reflexive, okay. So let's say we have R, a relation on A. To prove a relation is reflexive, you need to take an arbitrary thing out of that capital A. So let's call it little a. And show what? Yep, A is related to itself. Absolutely. Okay, reflexive was not an if-then statement. It was a for-all statement. The rest of these were if-then statements. So to prove it's symmetric, you assume the if, and the if was A related to B. And what do you show? B related to A. Transitive, what do you assume? Yep, A related to B, B related to C. Show A related to C. Yep. Now the details between the assume and the show completely rely on whatever the heck your relation is, right? You have to look back and say, oh, in this case, to be related means this, and work with that, okay? That's what's going to change with every single problem. You have to look at what it means to be related. So the absolute easiest example we did last time was the equal sign. Okay, the equal sign, there's nothing to show. A equals B, B equals C, duh, A equals C. But a lot of these, it's more intricate, okay, to go through and show. All right. Any questions on that? Because then we've got time for me to show you a very tightly related fact. Okay, cool. It is exciting. I wasn't sure if we'd had time for this. So here's our fact. Every partition of, and we'll just call it capital A, so that's whatever the heck our set is, every partition of A creates an equivalence relation on A. All right, so what do I mean by that? So here, let's say my partition is, I don't know, let's take a set of just a bunch of P's, okay? And I could have, again, 3 things in the partition. I could have infinitely many things in the partition, okay? So here's the relation we create. We say A is related to B if and only if A and B are in the same PI. All right, so let's make sure. Nope, this is well defined, right? I look at a set and anything in that set is related to each other, right? Because they're in the same thing. Now, in order for this to be equivalence relation, we do need that it's a partition. We're going to need that everything is covered and that it's disjoint. So let's see that. Let's outline that. So I guess we'll say outline. All right, let's think about reflexive. Well, I need to take a random A in capital A. What was the first property of being a partition? Yeah, the union of all the different pieces has to be everything. Okay, so since the union of the piece of i's equals capital A, little a is in piece of J, right? For some J, he's in at least one of them if the union is everything. So is A in the same set as himself? It's kind of silly, but yeah, so A is related to A. I had to make sure he was in one of them first, but once he's in one, yeah, he's related, he's in one, so he's related to himself. Okay. Symmetric. So now we'll assume A is related to B. What does that mean according to this specific relation? Oh yeah, you're getting too fancy on me. Now A and B are in PI for some PI, right? Or for some I even, we could say. So one of my things has both A and B. But if they're both in there, they're both in there, right? Order doesn't matter to a set, okay? So B and A are in that PI for some I, which means B related to A. So symmetric. Yeah, what's up? Correct. Big A is the universe. Yep.
And because A is related to B, you know that both A and B are in PI.
Mhm.
And if AB is in PI and so is PA.
Right, because sets don't care about the order of elements. If A and B are in there, then A and B are in there, B and A are in there.
Okay.
Yeah, if it was an ordered pair, I would be in trouble, right? Okay, so transitive. We'll assume A is related to B, B is related to C. All right, here's where we got to be a little careful. So the first one means A and B are in some PI, right? Second one means B and C are in some PJ. What property of partitions guarantees that those are the same thing? Yeah. So it's that pairwise disjoint thing, right? Their intersection is not empty, so they have to actually be the same thing. You guys see that? So B is an element, PI intersect PJ. So it's not equal to the empty set. PI equals PJ. So here's where we get A and C are both elements, and now I can use whichever way I want to call it. I'll call it PI, but PJ, same thing. Okay. So A is related to C. So you can see both properties of partition were important. I can't have reflexive without the union being everything, and I can't get transitive if they're allowed to overlap. Okay, so that's kind of cool. And this is what becomes important in math. For example, in algebra, when you have something like x squared minus 1 over x plus 1, what does your high school teacher have you do here? Factor and cancel the like things, right? Divide out by the x plus 1 and get x minus 1. Yeah. According to algebra, these are technically tiny bit different. Why? What's the difference between this function and this function? Yeah, so that first one, I technically can't plug in -1. I can't divide by 0. The graph of that would technically have a hole at -1. Okay, but in reality, who cares if I'm dealing with this line or the exact same line with the hole? We learn in calculus that if that limit is approaching the same on both, we can act like it's continuous, right? We can fill the hole and act like it's continuous. Okay, so in algebra, whenever you take any function that simplifies to x minus 1 and call it x minus 1, you're actually using equivalence classes. You're saying every function that looks like x minus 1, except maybe it has some holes that all go away if I simplify, I'm going to call them all x minus 1. You're grouping them into one class. Okay, so you can deal with the easiest member of the class. So that's one way you guys have already used equivalence classes without knowing it. That becomes important in upper level math if you could say all these things I'm grouping together because they have this property I want in common, and then you can work with the easier ones in it and draw conclusions. So that's where this comes in, is important. Does that kind of make sense, what we're saying? So kind of to give you a heads up of where we're going next, we are going to talk about functions next. Function is a special type of relation, okay, with special properties. And we're going to talk about words surjective and injective and bijection and stuff. These are going to come up for those of you not graduating in upper level math classes. Okay. Did you see bijection at all in probability? Did that come up? Those of you that had that already? No. So, but yeah, that will come up. So that will be important. But yeah, that's what we got left. Any questions? All right, well, that's good enough for today.